Hello everyone, welcome to our second lecture on electrostatics. So in our first lecture, we went through a basic introduction about electrostatics, Coulomb's law, then about electric field and electric displacement field. So in this lecture, we are going to discuss about Gauss law. Gauss law states that the net flux of an electric field E through a closed surface, that is integral of the electric field through the surface, is proportional to the enclosed electric charge. Now, the first term here, the net flux. What is flux? Flux can over. Now, when we have electric charges, these will generate electric fields. That is what we discussed previously. With these electric fields, we can show each of these fields using electric field lines. So in a space, there will be so many electric field lines. Now, if I consider electric field lines like these, and if these electric field lines are crossing, if these electric field lines are passing a certain area, so these electric field lines are passing a certain area, then electric flux psi is the number of electric field lines passing per unit area perpendicular to the considered area. So psi is the number of electric field lines passing per unit area perpendicular to the considered area. To the area. So for this considered area, how many electric field lines are passing perpendicular to that area? That is the flux. So if this area is not perpendicular to the electric field lines, what will happen? Then what we can do? So let's say we have a certain situation. Now electric field lines are passing like this, but with the perpendicular line, the considered area is having a certain angle. Now this is the considered area. Electric field lines passing through this area is not perpendicular to that area. So in that case, we can write net flux, or the flux psi is equal to E dot A. So here we know E dot A is going to be magnitude of E, magnitude of A cos theta. So if the area is directly perpendicular, then we can just take psi is equal to E times A. But if the area that we are considering is not perpendicular, then we need to consider the dot product to calculate the flux here. Now, what is the Gauss law states? Gauss law states the net flux of an electric field through a closed surface. Now, we know what is the flux, then see what is a closed surface. Now, closed surface, we can have some closed surface like this, that is enclosed in a volume or a surface area. Then Gauss law states the net flux of an electric field E through a closed surface, that is the integral of surface integral is proportional to the enclosed electric charge. Now we know what is flux. Then if I consider there are so many electric field lines coming through this closed surface, electric field lines may get closed surface then I will consider a small area segment like this. So area is in this direction, and the electric field going through that electric field lines crossing that area, I will say EI. Okay. Then if I want to consider all this closed surface, now first let's consider this psi here, flux due to this surface and flux due to this electric field line. So it is going to be, there's going to be a delta psi, that is EI dot AI. So again, I can write that EI. So this is a very small area segment, delta AI cos theta. Okay. Then in order to calculate the total flux, net flux of an electric field through a closed surface. Now, in order to calculate the total flux, what we need to do? We can take the surface integral of each of these flux through the all the surface. So what I will do is, I will take the integral of this psi. Now we have a area segment like this, another area segment like this, through the all the area segments. Okay. So we are going to take all the area segments. Then how these electric field lines are generated? How these electric field lines are generated? How to get all my electric field lines generated? So before going into this, I will discuss about that. So how these electric field lines are generated? Each of these electric field lines are generated. Electric field lines generated. What should be the source of this? What is the source of this each of the electric field line? So we need to have some charges in order to generate electric field lines. So in order to generate each of these field lines, there should be some charges enclosed in this closed surface. Then what can we say about the electric flux that is coming through the closed surface? Then major charges, flux electric field lines charges in the electric field lines in the flux. So what can we say about the flux? It's going to be proportional to the number of charges enclosed by the closed surface that we consider. So these electric field lines are generated due to each of these charges, and then we are calculating the electric flux. Therefore, electric flux is proportional to the first, it is proportional to the electric field, and that electric field is proportional to the charges enclosed by the considered area. Then we can say the proportionality constant psi is equal to 1 over epsilon naught Q total. Then psi is equal to Q total over epsilon naught. Okay. Now we can use these two equations here, psi Now we considered a delta psi. In order to calculate the total flux, net flux through a closed surface, we need to consider the surface integral over the closed surface dot E S. So initially we considered for this small area segment, what is the delta psi? The small flux that will be generated through this area. Then in order to calculate the total flux that will be generated through this closed surface, we need to do the surface integral of this each of the electric field segments by each of the area segment. So psi is equal to total net flux is equal to surface integral of E dot ds. And that we can say this psi, it is equal to, now we have this equation, and previously we obtained this relationship psi is equal to Q total over epsilon naught. Now this is the Gauss law that we are going to use. Gauss law states the net flux. So the net flux of an electric field through a closed surface, that is the integral of E over surface, is proportional to the enclosed electric charge. And the proportionality constant is 1 over epsilon naught. So this Gauss law is it is one of the four equations of Maxwell's law in electromagnetism. We are going to discuss that later. And this equation is first formulated by Carl Friedrich Gauss in 1835. And the electric flux, we discussed what is electric flux. It is defined as the electric field lines, electric field passing through a given area multiplied by the area of the surface in a plate perpendicular to the area. We can state this Gauss law in several different ways. Another statement of Gauss law is the net flux of an electric field through a closed surface is equal to the total charge enclosed divided by the permittivity. Total charge enclosed divided by the permittivity. So is this formulation of the Gauss law, is it clear? Any questions? We discussed what is the flux, and if the area that we are considering is not perpendicular to the electric field lines or the electric field, then how we can calculate the flux? That is E dot A. Then I considered a enclosed surface. So when there are several electric field lines coming through, we can consider for each of the area segment, what is the delta psi, a small segment of flux coming through that area, that is going to be EI dot delta AI. And then in order to generate these electric field lines, there has to be certain amount of charge within the enclosed surface. So this flux is proportional to the charges enclosed, total charges enclosed by this area. Then if I consider previous calculations, scientists have found that the proportional constant is 1 over epsilon naught. Then flux is equal to total charge enclosed by this closed surface over epsilon naught. And then with this equation, for the whole surface, I can calculate what is the net flux through this closed surface. So we need to take the surface integrate. We need to integrate each of these small segments through all the area, all the surface. So that is going to be surface integral of E dot ds, and that is also the flux. So flux is equal to Q total over epsilon naught. So this is the Gauss law. So we can write in this way or in this way. So psi is equal to either this part or this part. And also we can write this Gauss law by taking epsilon naught into this side. So epsilon naught times surface integral of the electric field is equal to total enclosed charge. Now what will happen? There are no charges enclosed in this area. If there are no charges enclosed in this area, then it will not generate any flux. Therefore, this surface integral is going to be 0. Okay. And so this is the integral form of the Gauss law, we can also write the Gauss law in differential form. So in differential form, let's say in this enclosed surface, we have several charges, a charge distribution. Charge distribution, with the charge distribution, we can calculate the total charge enclosed. Q total is equal to, what we need to do is, if there are a certain distribution of charges like this and the density is rho, then we need to do the volume integral of that charge densities to calculate the total charge enclosed by this surface. And now, from this equation, we know E dot ds surface integral is equal to Q total over epsilon naught. So now we know Q total is equal to volume integral of rho dV over epsilon naught. Then we can take this epsilon naught to this side. So we have epsilon naught surface integral E dot ds is equal to volume integral of charge density over the total volume. Then we need to use this divergence theorem. So I'll go back to the initial slide set. Divergence theorem. In the divergence theorem states the normal surface integral of a vector function f over the boundary of a closed surface. So in here we have surface integral of a vector function over the boundary of the closed surface, which is the flux across the surface S. So flux across the surface is equal to the volume integral of the divergence of the function over the volume V enclosed by the surface. So that is the theorem. So what this theorem states is, when we have a surface integral, so if we just do integral once, අපි එකපාරක් integrate කළොත් අපිට මොකක්ද මම කියන්නම්. So I will consider x-axis. Okay, so on the x-axis there is a certain function like these points. So if I integrate these values, if I add all these values, if I add all the continuous values all together, then we are going to get a line. So that is, when we integrate once, we are going to get line. Then when I have another values here, another axis here, then we can have a certain function through the 2D space. Then for this line, if I keep integrating through this y-axis, then we are going to get the surface integral. So by integrating twice, we are going to get the surface integral, same like that we denote here, f dot ds. And in the divergence theorem states that it is equal to the volume integral. So volume means we are going to add another axis, z axis. So when we integrate this area through another axis, we are going to get a volume. So that is equal to del dot f dv. So this is the divergence theorem. So we are going to apply that divergence theorem here. So here we have a surface integral. So we can write that in a volume integral. Once we write this side also in a volume integral, then we can consider if the both of the limits are equal and the same volume that we are considering, then we can equal these integrals. So we can write this side as a volume integral. So we need to consider divergence of the considered vector field. divergence of the considered vector field is E, and it is equal to volume integral of rho d epsilon naught. So now on both of the sides we have a volume integral. So with that, so here volume integral, and here also the volume integral for the same volume. And if the volume, like the considered limit, is also the same, then we can write del dot E. So epsilon naught is a constant. dV is equal to volume rho dV. Now the volume and the limits are the same. Then epsilon naught times del dot E is equal to rho. So when the volume is the same, then we can take this. We can say the values inside this volume integral is the same. Now with that, we have the differential form of the Gauss law. Del dot E is equal to rho over epsilon naught, or we can say, so this part is the divergence of E is equal to rho over epsilon naught. So this is the differential form of the Gauss law. This is one of the Maxwell's equation, states that the divergence of the electric field at any point is just the measure of charge density there. So divergence of the electric field at any point is the measure of charge density there. So this is the Gauss law in differential form. And also we know electric displacement field D is equal to epsilon naught or epsilon times E. Therefore, from here I can write epsilon times E is equal to rho. Therefore, divergence of electric displacement field is equal to rho. So this is another way that we can state Gauss law in the differential form. Okay. Any questions up to this point? ඔයගලන්ට තේරෙනවද මේ Gauss law එක කොහොමද භාවිතයට එන්නේ? ඊට පස්සේ අපිට මේක එක්ස්ප්ලেইন කරන්න පුළුවන් කොහොමද net flux එකත් එක්ක පටන් අරගෙන ඊට පස්සේ differential form එක තියෙනවා, integral form එක තියෙනවා. Any questions up to this point? So here a question is given. Suppose the electric field in a region is given by this value. So E is equal to K R cube, the direction of R in spherical coordinate system. In spherical coordinate system, and K is a constant. Find the charge density rho and also find the total charge contained in the sphere of radius R centered at the origin. So now here we need to use the spherical coordinate system. In a spherical coordinate system, now most of the time we are using this Cartesian coordinate system. In the Cartesian coordinate system, what we have is x, y, and z components. So in a Cartesian coordinate system, we will have, if I want to denote a certain point in the space, then we denote that using x, y, and z components. But also we have this plane polar coordinates and cylindrical polar coordinates. and also this spherical polar coordinate system. So here we need to use the spherical coordinate system. In a spherical coordinate system, what is happening is, now in a Cartesian coordinate system, we are considering x, y, and z. But in a spherical polar coordinate system, if we want to denote a certain point in the space, so we have this x, y, and z axis. But to denote a certain point in the space, the values that going to represent that point are the r value is the from the origin for the considered point. What is the distance? So we are going to use r. Then theta from z axis. What is the angle there? And the angle here from the x-axis psi. So in polar coordinate system, those are the values going to use. So in Cartesian coordinate system, we are going to use x, y, and z. In a polar coordinate system, we are going to use r, theta, and psi. So there are two angles and one distance in a polar coordinate system. Now here in a so it's a spherical polar coordinate system. In a spherical polar coordinate system, we are going to use r, theta, and psi. Spherical polar coordinate system. So here we need to consider this electric field in a spherical coordinate system and find the charge density rho. First, we need to calculate the charge density rho. So the divergence, previously we used this divergence formula in Cartesian coordinate system. So this del operator dot a is going to be dabba or dabba x, a x, dabba or dabba y, a y, dabba or dabba z, a z. But when we change the coordinate system, this operation, the divergence formula is going to change. Now we need to use this divergence formula in spherical coordinate system. So in spherical coordinate system, we have a little bit long equation 1 over r square dabba over dabba r r. So AR is the component of this R. Then we have A theta and A psi. Components of R, theta, and psi. Now, in the question, it is given E is equal to K R cube, the direction of R. Then we can use the differential form of Gauss law to calculate the charge density here. So del dot E is equal to rho over epsilon naught, and rho is equal to epsilon naught times del dot E. Now, since we are using this spherical coordinate system, we need to use this long equation. But if we look into this electric field, what can we do? So we can simplify this equation when we look into this electric field. මේ electric field එකට දිහා බැලුවාම how can we simplify this equation? Any suggestion? So do we have a theta component and psi component? Do we have a theta component and a psi component? We don't, right? So we only have this R component. Therefore, what can we say about this dabba or dabba theta component and dabba or dabba psi component? So both of these components are going to be 0. This one and this one are going to be 0. Then the only remaining part is going to be this. So we can write epsilon naught 1 over r squared dabba over dabba r squared. Now the AR component of R, we have K R Q. Okay. So simplify this one and calculate the charge density. So we can write charge density is equal to epsilon naught times 1 over r squared dabba over dabba r K r to the power 5. Do this partial derivation and see what is the charge density. So what is the answer? Now, if you do the calculation correctly, you should be able to get this answer. Okay, so check whether you are getting this answer as the charge density in the given electric field here. Then also we need to find the total charge obtained in the sphere of radius r. So let me know any questions up to this point, or have you got the same answer? ඔයගොල්ලන්ට මේ answer එක මොනවද? Okay, so then try to calculate now you know the charge density, then find the total charge contained in a sphere of radius r centered at the origin. So now we know the charge density, and charge density is proportional to r to the power, r to the power 2. Then we need to calculate the total charge if we have a certain sphere with the radius r. Find the total charge contained in a sphere of radius r centered at the origin. Once you know the charge density, what you need to do? When you know the charge density, in order to calculate the total charge contained in the sphere of radius r, you can do the volume integral here to calculate the total charge. Try that one. So there are two methods to calculate the total charge. One way is to use the Gauss law in this integral format. So we know the electric field is given and total charge is equal to epsilon naught times surface integral E dot ds. So now we know this E, it is equal to KR cube, and in order to take the total surface, not take the total surface, we can take the surface of this or the sphere. So that is going to be 4 pi r square. Then the total charge enclosed by this sphere with the radius capital R, it's going to be 4 pi epsilon naught k r to the power 5. Another method that we can do is, once we know the charge density, we can take the integration uh, along this sphere to calculate the total charge enclosed by the sphere. So both of these answers should be same, and you can calculate the total charge contained in a sphere of radius r centered at the origin using these two methods. Okay. So check whether you are also getting the same answers. There are like mainly two methods are emphasized here. One is to use the Gauss law in integral format, and then the second method is to detect integration the charge density. So during today's lecture, we went through basically how this Gauss law formulates and few example questions from this Gauss law. We are going to continue our discussion in future lectures, and thank you very much.